Okay, so today we're going to do maybe the most interesting application along the lines of volumes and areas and things like that. And so what we're going to do today is called surface area. Surface area. Surface area. Okay, and so the idea is this: that we are going to have some sort of some curve like this, and then we're going to rotate it. We're going to rotate it around an axis. We'll rotate it around an axis. And the question is, how do you, what is the area, what is the surface area of that object, right? What's the surface area of that object? Okay. Please put any phones away. No phones. I don't know if anybody's using phones. No phones in class, please. Yeah. Okay. So what's the idea? You can guess what. There's sort of like a calculus philosophy, and the calculus philosophy says, if you can't do a hard problem, then just think of the easy problem that you can do, right? Try to find an easy problem that get an easy problem, and then take the limit of those easy problems and turn it into the actual answer of your hard problem, right? So again, so we'll say, well, I don't know how to find the area of this thing, but what I can do is I'm going to break this up again into straight lines like this. Okay, I'm going to break this thing up into straight lines, and I'm going to rotate those guys around, right? So here, I end up like this, right? And I rotate those things around, right? I get this straight line, right? I get these objects. Oops, lining up with that. Rotated the wrong way. Anyway, okay, you see what I mean, right? Sorry, it should be kind of the other way. Should go like this, right? You see, and so the objects that I get, okay, and so what are these objects? Well, these objects, as you see, are just pieces of cones, right? They're pieces of cones, right? Like if you have something like this, and right. So what you get are these pieces of cones, right? So you have this line here, and you've rotated it around an axis here like this, right? If you had the full straight line, right, then you would have a cone, right? And so the question is then, how do you figure out this area, right? Can you figure out this area? And this is just this becomes an elementary problem. Okay, so you need to figure out the surface area of this piece of a cone. You need to figure out the surface area of this piece of a cone, right? Okay, and here's how we're going to do it. We say, okay, well, if you have a cone, okay, if you have a cone and you look at the surface area, so the let's say the cone has this. Suppose this length is L, the length of this side is L, and this length is the radius here is R. Okay. Then the surface area of the cone actually turns out to be pi R L. Turns out to be pi times R times L. So this is the cone. There's no bottom. There's no bottom to this cone. Okay. So we're not adding on the area of the base, the area of the base here, but just the area, the surface area at the top turns out to be pi R L. Okay. So so now suppose we have something like this, right? We have this length is L1, and this full length here is L2, and say this radius here is R1, and this radius here is R2. Okay, right? Then what's the area of this? What's the surface area of this thing down here? Right, and you just subtract, right? You subtract the big cone, the small cone from the big cone. Right? You just take the surface area of the big cone and then subtract off the surface area of the small cone, right? And you get the surface area of this piece here, right? So you get pi R R2 L2 minus pi R2 L1, right? Right. Sure, of course, right? That's easy. Okay. We can simplify this a little bit by. So we're going to simplify it by using an observation. Okay. So observe. If we draw similar triangles here, right? This is R1. This is R2. This is L1. This is L2. Right, so you know that L1 is to R1 as L2 is to R2, right? And that means that's the same thing as saying R2 L1 equals R1 L2. Right, by similar triangles. Okay, so I'm going to rewrite this. Okay, I'm going to rewrite the formula for the area of that thing by, well, first I'm going to factor out a pi. Okay, so R2 L2 minus R2, whoops, that should be R1 L1. Minus R1 L1. Right, so you factor out a pi, and then we're going to do something funny, which is we're going to subtract off, no, we're going to add in, sorry, R2 L2 plus R1 L2. Okay, and then we're going to subtract off R1 L2. R1 L2, R1 plus R2 L2, R1 plus R2. Yeah, good. Okay. Yeah, one more.
It should be R2 L1. The third.
This one? This one? No. See, what I'm yeah. So what I'm doing is I'm throwing in. But it will change. It will change to that in a second. It will change to R2 L1 in a second because R1 L2 is R2 L1. Okay. So, but first, before we get there, see what I'm doing? I'm adding in 0, right? I haven't changed anything. I've subtracted R1 L2. I've subtracted R1 L2 and I've added R1 L2. So this doesn't change anything, right? Is that clear? Doesn't change anything. And then I'm going to use the observation here to rewrite R2L2 plus R1L2 minus R2 L1 minus R1L1. So R1L2 is R2L1 from the observation. Okay. And then you notice that this is R1 plus R2 times L2. And this is R1 plus R2 times L1. Right? Right? And so we can simplify this further. This becomes pi times R1 plus R2 times L2 minus L1. Pi times R1 plus R2 times L2 minus L1. Right? Or I can write this as 2 pi times R1 plus R2 over 2 times L2 minus L1. Okay, so it's the average 2 pi times the average radius, right? So the average radius is going to be the radius in the half in here, right? R1 plus R2 over 2, that's this half radius, the average radius, times L2 minus L1, right? This thing here is L2 minus L1 times this height, right? So let me write it up. Here, if I have something like this, and the radius here is R1, and the radius here is R2, and this is some length, L2 minus L1, right? Then the surface area of this object, right? Surface area is going to be 2 pi times the average radius times this height, times this length. I'm just going to call that length L. Okay. Times that length L. So 2 pi times the average radius times L. In other words, it's the same as the surface area of a cylinder, right? It's the same thing as the surface area of a cylinder where the radius is R1 plus R2 over 2 and the height is L. Right? 2 pi R times L is the surface area of a cylinder. So the area of this is the same as if we took this thing and straightened it out. Right? We straighten it out, we get this thing, and the surface area doesn't change. Okay. Right? If we took these things as the middle point and just sort of like pulled it this way somehow, right? Then the surface area doesn't change, and the surface area of this object is the same as the surface area of the cylinder. Okay. Okay. So that's the elementary school mathematics part of this, right? And now we need to combine this with the notion of limit to get the surface area of our rotated graph. Okay. Any questions about this part? It's just it's just geometry and arithmetic, right? Just geometry and arithmetic. Okay. So now. Okay, So now what we're going to do is we have this thing, right? You have this thing, and you rotate it around some axis, right? You rotate it around some axis, whoops, right? You do your approximations, right? You get the areas, you get the surface areas, sorry, of these objects, right? Right? You get the surface area of these objects, and then you take the limit, right? Right, so maybe you can guess what happens in the limit. Let's say that this is y equals, this is the graph of some function from a to b. Okay, and suppose we rotated it around the x-axis. Okay, right. So what are we going to get? What's going to happen? Can anyone guess? Can anyone guess? Let's look at the pieces, right? So let's say this is x0, x1, right? What's the surface area of this first piece? Well, it's going to be 2 pi times the average radius, right? The average radius is going to be f of x0 plus f of x1 over 2, right? That'll be the average radius, right? Here. And then multiplied by that length, right? Well, what's that length? That length is going to be the square root of x1 minus x0 squared plus f of x1 minus f of x0 squared, right? 2 pi average radius times the length of that length here. This is f of x0, this is f of x1. Right? And we're going to sum as k goes from 1 to n of, let me just change these guys, sorry. K minus 1, K minus 1, K minus 1. Right? We sum all those things, and that is our approximation. Right? And then you take the limit. Let n go to infinity. And what do you get? You're going to get the integral from a to b. You do the same thing we did last time. You're going to divide by xk minus xk minus 1 squared, and you're going to multiply, I'm sorry, the square root of that, and you're going to multiply it by that delta x. Right? Okay. And then in the end, you're going to get 2 pi f of x, right, times the square root of, what's this thing here? Somebody saying it? Who's saying it? Yeah. 1 plus? Exactly. Yeah. Very good. Right? 2 pi f of x square root of 1 plus derivative squared dx. Right? The same thing. We saw this term. This term here we saw last time. Right? And it turned into, remember what happened, you divided, you got 1, this thing was the derivative squared, this thing turned into the derivative squared, and then this thing turns into your dx. Right? Okay? Okay. So that's the surface area. That is the formula for the surface area of the graph. Surface area of the graph rotated around the x-axis. You know, the sort of infinitesimal way of thinking about it is that this thing here is the arc length, right? This thing here is a infinitesimal arc length, right? This thing is, it's some tiny arc length here. Okay. It's the length of an infinitesimal piece of your arc, right? And then you multiply that thing by 2 pi f of x, right? That gives you the area of the infinitesimally short cylinder, right? So 2 pi f of x, 1 plus f prime x squared dx, right? This thing is the arc length of an infinitesimal piece of your arc, right? And then you multiply that thing by 2 pi f of x, right? And that will give you the surface area of, you know, a infinitesimally short cylinder, right? You've taken this tiny little thing and you rotated it around, right? And you get this cylinder, right? The length of this thing here is 1 plus f prime squared dx, right? And the radius of the cylinder is f of x, and so you get, you know, 2 pi r times the height of the cylinder, right? This is the right. The height of your cylinder is this thing. Okay, and then you sum all those things together from A to B, and you get the sum of all those areas of the cylinders, and that gives you the whole thing. Okay. So that's the infinitesimal view of this. Okay, let me make one observation. Notice, if we had something like this, okay, y equals f of x again, okay, and we rotated that thing around the, instead of rotating it around the x-axis, we rotated it around the y-axis, right? Then the surface area from A to B, the surface area then would be integral from A to B, 2 pi, what's the radius now? X, right? It's not f of x, it's x. You get 2 pi x, 1 plus f prime x squared dx. Right? 2 2 pi x, right? Because you're not rotating it this way, you're rotating it this way, right? And so you have this little piece, right? This little piece here at x, right? This is, and you rotate it around, right? Well, the radius is x, and the infinitesimal height is still this 1 plus f prime x squared dx. Right? Infinitesimal height is still square root of 1 plus f prime x quantity squared dx. So you get the surface area is this. Yeah, basically over here what you have is 2 pi y, right? Here you have 2 pi y, and here you've got 2 pi x, right? Okay. Let's do an example to make this concrete. So here's one. Y equals sine pi x. X ranges from 0 to 1, right? And you rotate around the x-axis. Okay. So you've got you've got 0, 1. You've got this thing here. And you rotate it around the x-axis, right? And you get this, you get this surface here, and you're wondering what the area of the surface is. Okay, take 1 minute and write down the integral. Okay, turn to somebody next to you and say what you got. Talk with these guys in front of you. Okay, who can tell me what it is? Should be easy. right? This, if you, right, this should be completely easy. How do you, somebody tell me what it is. Sri Chencheng, how about you?
The surface area is integral from 0 to
Uh-huh.
2 pi sine pi x square root 1 minus cosine square pi x dx.
Almost. You missed one thing. What's missing? What's missing? There's a pi. There should be a pi squared, right? Because when you differentiate, when you take the derivative of the sine pi x, you should end up with pi cosine pi x. Right. So then you get that square here. Okay. Plus, yeah. Plus. Okay. Everyone get that? Everyone get that? Okay, here's another one. Here's another one. Any questions? Sounds like there are questions. No? Okay, here's another one. Y equals 1 minus x squared, 0, x, 1, and you rotate around the x-axis. Okay. So you have this parabola, right? You have this downward going parabola, 0, 1. You rotate that thing around the x-axis, and you want to find the surface area of that. Okay. So again, take 1 minute and just write it down. Again, it should be just like that. It should be easy. Okay, turn to somebody nearby and say what you have. Should be easy again. Okay, okay. Who would like to tell me what it is? Me, Payton. How about you? You didn't get it?
Yeah.
Okay, that's all right. That's all right. Wang Qingchao, how about you?
minus 1 to 1.
Minus 1 to 1.
2 pi multiply 1 minus x squared.
2 pi 1 minus
4x squared.
4x squared.
2 pi multiply 1 minus x. 4
I'm sorry, say it a little.
1 minus x squared.
1 minus x squared. 1 minus x. X squared like that?
Yeah.
And dx. Okay. How did you, so what is this, so this thing here is